So let's learn a little bit about what makes something an acid or a base. So we're going to look at two different definitions for acids and bases. And the first one is called the Arrhenius model, or the Arrhenius acid or base model. And this is the most traditional model of an acid or base. In the Arrhenius model, an acid is a compound that donates H+ ions or hydrogen ions into solution. So when you have an acid in solution, it's going to break apart and it's going to donate H+ ions or hydrogen ions into the solution. So two examples would be hydrochloric acid. So when that dissociates, it donates an H+ and a chlorine ion. And the other one would be hydrofluoric acid, which is HF, and when that dissociates, it donates its hydrogen ion, and then it also has the fluorine ion. So that's an acid according to the Arrhenius model. A base, according to the Arrhenius model, is a compound that donates hydroxide ions, or OH ions, into solution. So two examples of Arrhenius bases are lithium hydroxide, which when it dissociates would turn into lithium ion and hydroxide ion, so there's the hydroxide. And the other example would be barium hydroxide. When it dissociates, it donates its barium ion, and then in this case, two hydroxides. But the bases donate the hydroxides, the acids donate the hydrogen ions. So that's how you can tell the difference between an acid and a base according to the Arrhenius model. The other model that we're going to look at is called the Bronsted-Lowry model, and this is the most versatile model of acids and bases. In this case, an acid is still a compound that donates hydrogen ions to solution. So we're still donating the H+ if it's an acid. However, the difference comes when you look at the bases. Bases, according to Bronsted-Lowry, are compounds that accept hydrogen ions from the solution. So we're looking at what compounds are giving the hydrogen ions and what compounds are accepting hydrogen ions. So we're not looking at hydroxide at all according to Bronsted-Lowry. We're looking at, is a hydroxide being donated or is a hydroxide being accepted? And in this case, we're looking at a relationship between some compound and water. So the one that we're going to use in our example is ammonia. So NH3 reacting with water, and it's going to turn into the ammonium ion, which is NH4+, and the hydroxide. So let's go through this and label what is our acid and what is our base. Well, in order for NH3 to turn into NH4+, the NH3 needed to accept an H+, and it's actually going to get it from the water. That if it's accepting a hydrogen, that means it's going to be the base. And where did that hydrogen come from? Well, that hydrogen came from our water. That makes our water, since it donated the H+, that makes this the acid. If we look and go the other way, our NH4+ would be the one to donate the hydrogen ion to get back to NH3, so this would also be an acid. And our OH- to get back to our water would have to accept a hydrogen ion, which makes it a base. So we can also look at these. You'll see them frequently called conjugate acids and conjugate bases. So if our NH3 was our base at the beginning, that means at the end it's going to act like an acid. Whereas our water donated the hydrogen, so it acted as an acid at the beginning. What it ends with is a compound that's going to act as a base. So they go in pairs. So what's starting as a base then it turns into an acid, and so that would be called its conjugate acid. And what originally started and acted as an acid would form what's called the conjugate base. So in this solution, we have two acids and we have two bases, or two compounds that are acting as acids and two compounds that can act as bases. Acids and bases work by dissociation in solution. So that means they become acids and bases based on how they interact in solution. So we have two types of acids and bases. We have strong acids and bases, and that means it completely dissociates. So that means the compound completely breaks apart. One of our strong acids is hydrochloric acid. It completely breaks apart into its H+ and chlorine and Cl- ions, into its hydrogen and its chlorine ions. This means that our concentration of hydrochloric acid is the same as our concentration of our hydrogen ion because it's completely broken apart. Since our hydrochloric acid has turned completely into its two ions, the concentration of the original acid is equal to the concentration of just the hydrogen ion. And that's going to be important later when we talk about how to calculate pH. The other type of acids and base is called a weak acid or a weak base, and these do not completely dissociate. So that means they don't completely break apart into their two ions. It means the original compound and the ion are existing at the same time. And so our example we went through for our Bronsted-Lowry is NH3 reacting with water to form NH4 plus and OH minus. And that's a weak acid-base sort of reaction. And we draw the double arrows because it means it's going back and forth between the two. There isn't a complete dissociation when it reacts with water. And that means we cannot assume that the concentration of our base is equal to the concentration of our hydroxide. We cannot make that assumption for a weak acid or a weak base. You can only assume that the concentrations are equal for strong acids and strong bases. So we really don't have that many strong acids and strong bases. We have 6 strong acids, and they're written here. And then we also have 7 strong bases. So the hydroxide compounds of everything in group 1 on the periodic table. And then we have 2 from group 2, calcium hydroxide and barium hydroxide. So these aren't there necessarily for you to memorize right now for this class, but you should be able to recognize that when we're working with hydrochloric acid, it's going to completely dissociate. So like most things we've done so far this year, we've drawn particle diagrams for a lot of the scenarios we're representing. So we're going to draw particle diagrams to represent strong acids and weak acids and strong bases and weak bases. So first, let's review what it means to be strong and weak. So if something is strong, it completely dissociates. This means that it's going to completely break apart into its 2 ions. So you're not going to have any of the original compound left. If something is weak, whether it's a weak acid or a weak base, it's going to not completely dissociate. So it does not So a weak acid or a weak base does not completely dissociate. This means that you're going to see both the original compound and the 2 ions in solution. Okay, so now that we remember strong versus weak, let's talk about acids versus bases. So acids are going to produce H plus ions, and bases we can think about kind of in 2 ways. It's going to produce OH ions, or it can accept H plus. So no matter what, an acid is going to donate an H plus. So you're going to see an H plus ion floating around. A base, you're either going to see OH ions floating around, or you're going to see that, or you're going to see that they accept H pluses or hydrogen ions. So let's look at a couple of examples. So my first example is HNO3. So we kind of have to decide, is this an acid or a base? Is it strong or is it weak? Okay, well HNO3 we know is on our list of strong acids. Which means we're going to see our HNO3 dissociate, and we're going to see it produce H plus ions. So when we're drawing a particle diagram for this, so if I have my box, I'm going to have my HNO3, 3. That's going to completely break apart into its H plus ion and its NO3 minus. So in solution, I'm going to see H pluses and NO3s. And they're going to be in a 1-to-1 ratio. So So if I were to look at this particle diagram, I would know that it's an acid because I see H plus ions floating around. And I would know that it's strong because I don't see any HNO3. All I see are the two ions. Okay, let's look at another example. I'm going to leave my box. Let's look at C2H5OH. Okay, so C2H5OH is an acid, and it's not on our strong acid list, which means it's going to be a weak acid, which means that it's not going to completely dissociate. So when we see this break up, we're going to see our C2H5O minus. We're also going to see H plus, but we're also going to see our original compound. So I'm going to see some C2H5OHs, but I'm also going to see some H plus, and I'm also going to see some C2H5O minus. So if I was given this particle diagram and I'm trying to decide if it's strong or a weak acid or a base, I see H pluses, that means it's an acid, and I see ions, and I see the original compound, which means that it's weak. Okay, let's do another one. So for my third example, I want to look at KOH, potassium hydroxide. Now, potassium hydroxide is on my list of strong bases. So that means it's going to completely dissociate, and it's also going to produce OH minus, or hydroxide. So we're going to see potassium ions, and we're going to see hydroxide ions, or OH minus. We're not going to see any potassium hydroxide because it completely dissociates because it's a strong base. And again, these are going to be in a 1-to-1 ratio because they're in a 1-to-1 ratio in their formula. So if I have 3 potassium ions, I have to have 3 hydroxide ions. Now, if I was given this particle diagram, I would know that it's a strong base because it completely dissociates. I don't see any of the original compound. And I also see OH minus, or hydroxide ions, so that tells me it's a base. Let's do one more example. So if I have NH4OH, or ammonium hydroxide is a base. It's not on my list of strong bases, so it's going to be a weak base. Which means I'm going to see 3 things in my particle diagram. I'm going to see my ammonium hydroxide, I'm going to see my ammonium ion, and I'm going to see my hydroxide ion. So I'm going to see NH4OH. I'm also going to see NH4 plus. And I'm also going to see OH minus. So if I was given this particle diagram, I know that it's a base because I see the hydroxide ion. I know that it's a weak base because I see ions and I see the original compounds. So that's how we can use particle diagrams to represent strong or weak acids or strong or weak bases.